All right, so I'm going to be talking about algorithm configuration for combinatorial partitioning problems. This is joint work with Nina Balkin, Vaishnav Nagarajan, and Ellen Bidersik. Okay, so imagine we have some NP-hard problem like clustering, and we have a very specific application in mind. Say we want to do protein sequencing by function. Okay, so there are tons of heuristics for clustering. There's k-means plus, there's single linkage, and all of these algorithms are really different from one another. So how do we find the best algorithm for our specific application? Okay, so in theoretical computer science, people analyze algorithms by their worst case complexity. So how does the algorithm do over the worst of all possible instances? Another thing you can do is think about the average case complexity, which is how well the algorithm does over a uniform distribution of all problem instances. But maybe since we have one specific application in mind, what's most natural is to think about our application as a distribution over clustering instances. So maybe protein sequencing clustering instances look a certain way, and we have some that can be a distribution. So we want to find the best algorithm for that distribution. So this is what I'm going to be discussing in this talk. Okay, so actually there's a lot of work on this in practice. There's the famous SATzilla algorithm, which won a bunch of SAT contests by piecing together a bunch of 7 state-of-the-art SAT algorithms. And when a new instance came in, it just figured out which SAT algorithm to run. And it won a bunch of awards in SAT competitions. Okay, but very little theoretical analysis is known for this problem. Until very recently, there's a nice paper by Gupta and Roughgarden, which came up with a cool framework for studying this problem theoretically. So now I'm going to explain that framework, and then I'll get to my results. Okay, so in the framework, we have some family of algorithms that we pick. It could be an infinite family. And then we have some performance metric. Let's just think about approximation ratio for this talk. And then we assume there's some distribution over problem instances corresponding to our application. And this is going to be unknown to us. So what would be ideal is if we can pick the best algorithm from the class for our distribution, but we don't even know the distribution, so this is a bit too much to ask. So instead what we do is we sample from the distribution and then find the empirically best algorithm and hope that it's close to the optimal over the distribution. So there are a couple questions about this framework that naturally arise. The first one is, how do we know that the empirically optimal algorithm is close to the optimal over the distribution? This is just a sample complexity question. How many samples do we need? And then the second question, remember there could be an infinite number of algorithms. So how can we efficiently even find the empirically best algorithm? Okay, so it turns out the first question, we just can use standard VC dimension bounds to get the answer right away. Okay, so now I'm going to get to our results. So something to point out is that the crux of this work is finding rich, expressive families of algorithms that also have VC dimension that's not too high. So now I'm going to get into clustering. So to find a rich class of clustering algorithms, I'm first going to explain some paradigm for clustering. Just think about k-median clustering. The actual objective isn't so important. Okay, so this is going to be a merging and pruning paradigm for clustering. So we start out with all the points. All the points are just going to be singleton sets, and then we're going to iteratively merge the two closest sets in each round until we have just a huge set with all the points at the root. I'll get to what I mean by closest in just a second. And then the second step is going to be the pruning step. We use dynamic programming to find the best k-clustering from the tree. Okay. So now what do I mean by merge the two closest sets? So there's a lot of ways to do this. So one way is the popular single linkage approach, where you look at the two closest points in the two sets. And complete linkage is also a common algorithm where you look at the maximum distance between any 2 points in 2 sets. So now I can define our large family of algorithms, which is going to be a spectrum between single and complete linkage. So there's a parameter alpha from 0 to 1. Alpha equals 1 is going to be single linkage. Alpha equals 0 is complete linkage. And then in between is going to be some hybrid of the two. Okay, so now we have an infinite family of algorithms. And we can show that the pseudo-dimension of this class of algorithms is theta log n. I'll just give a really quick idea of the upper bound. So it turns out if you analyze the decision points in the algorithm, we can show that there's just n to the 8th intervals from 0 to 1, such that if you take any alpha, if you fix some interval, run alpha linkage for any alpha in that interval, the output for the algorithm is going to be the same. So then we can use that fact to show that the pseudo-dimension is log n. By the way, pseudo-dimension is just the real valued equivalent of VC dimension. Okay. So, and then the lower bound is too technical for a 10-minute talk. Okay, so also this also, the proof implies a way to find the empirically best algorithm by just, it turns out it's not too hard to compute these intervals, and then we just pick one alpha from each class and pick the alpha that leads to the best empirical performance. Okay, so now I'm just going to briefly talk about max cut. I thank the organizers for putting my talk right after a talk about max cut. So remember, we have some graph and we want to find the maximum cut in the graph. So also our results are for generally for integer quadratic programs, but I'm just going to stick to max cut for this talk. Okay, so we are going to do a SDP approach. And we have varied algorithms by how we round this SDP. So it turns out there are a bunch of different ways to round the SDP. And each rounding is a different algorithm. So we're going to use the famous approach where we project to a random hyperplane. And then after we do that step, there's many different ways to round. So we're going to use the Feige-Langberg approach where we have this rounding function here. So if the value is really small, we have some threshold. If it's really high, and in the middle, it's some linear relation. This is called the S-linear rounding functions. So again, we can show the pseudo-dimension of this class is theta log n. Some idea for the upper bound of this proof is that if we take apart the objective function, we can show that it's just n plus 1 piecewise quadratic components, and then that implies that the pseudo-dimension is theta log n. And just as in clustering, this also implies a computationally efficient algorithm. If we compute the quadratic components and then solve for the alpha that gives us the best performance on our sample. Okay, so future work is looking at other rich families of algorithms and trying to show they have low pseudo-dimension, looking at other problems. And then also in this talk, I only mentioned families of algorithms with log n pseudo-dimension. We also know of some families with pseudo-dimension n, but it turns out we don't know how to efficiently find the empirically best algorithm. So it'd be cool to find new techniques to efficiently compute the empirically best algorithm. Okay. And I'm going to be presenting a poster tonight, so if you have questions, come see me tonight. Thank you.
Questions? Shai.
Yeah, I like the idea that the family of clustering algorithms you consider, they're all linkage-based algorithms. They all ignore, for example, requirements of balance between the size of clusters. So do you have in mind any family that will include things like k-means that also take into balance requirements between sizes of clusters?
Yeah, that's a good question. We only considered linkage-based for this work, but I think it would be great follow-up work to consider much different clustering algorithms.
More questions? Okay, let's thank Colin again.